Just take a second and look at this. It's the Whirlpool Galaxy. And every single one of those little points of light isn't just a light, it's a sun. Many of them probably have their own families of planets. We're talking billions of stars, all swirling together in this amazing cosmic dance. So you have to wonder, right? What in the universe is powering all of that light? And what kind of story does each one of those stars have to tell? Well, that's what we're going to do today. We're going to trace the epic life of a single star, from its fiery birth all the way to its incredible, spectacular death. All right, so our story actually starts not with a big bang, but in the cold, quiet, dark parts of space with a really, really slow but absolutely enormous collapse. So I want you to picture a gigantic, freezing cold cloud of gas and dust that's just trillions of miles across. Now, over millions of years, gravity just patiently does its thing, pulling the densest parts of this cloud closer and closer together. And as it all collapses, it starts to spin faster and faster, sucking in more and more material until you get this super dense, blazing hot core. This is what we call a protostar. It's like a star's nursery. Now, as this protostar keeps collapsing under its own massive weight, the pressure and the temperature in the center just go through the roof. I mean, they skyrocket. And when that core hits about 10 million degrees, which is just insanely hot, something amazing happens. Nuclear fusion kicks in. Hydrogen atoms start slamming into each other so hard that they fuse together to create helium, and that process unleashes a tremendous amount of energy. And right there, at that exact moment, a star is officially born. Okay, so there's this really cool rule in physics called the virial theorem that's basically running this show here. Think of it like a cosmic energy budget. As gravity is crushing that protostar, exactly half of all that energy gets trapped inside, heating the core up to those wild temperatures you need for fusion. And the other half? Well, that's the cool part. It escapes into space as radiation, and that becomes the very first light we see from a brand new star. So you might be thinking, okay, are all stars these huge, bright things like our sun? And, it's a fair question. But the truth is, not at all. Actually, the big, bright stars like ours are the cosmic oddballs. They're the exception, not the rule. And this chart here, this is called the initial mass function, and it basically proves it. Just follow along. As you move to the right on this chart, the star's mass gets bigger. But notice how that line just plummets downwards? That's telling us something incredible. For every single giant, bright star the universe makes, it churns out hundreds, maybe even thousands of smaller, cooler, and much dimmer stars. Yeah, turns out the cosmos really likes to build small. Okay, so once that fusion engine is fired up and running smoothly, the star enters the longest, most stable phase of its entire life. We call this the main sequence. Now, for pretty much its whole life, a star is locked in this constant, epic, high-stakes tug-of-war. On one side, you've got the crushing force of gravity, relentlessly trying to smush the star down to a single point. But fighting back from the inside is all that fusion going on in the core, creating this powerful, explosive outward pressure. And for billions of years, as long as these two forces are in a perfect stalemate, the star stays nice and stable. So what's the fuel for this whole operation? It's hydrogen. Simple as that. A star like our sun is about 70% hydrogen, and it spends its life fusing that hydrogen into helium. That's the process that releases all the energy, all the light and heat that makes the star shine. Just think about our own sun. It's been doing this for about 4.5 billion years, and it's only about halfway through its fuel supply? But here's the thing, it can't last forever. Just like the gas tank in your car, that hydrogen in the core is eventually going to start to run low. And this is where things get really dramatic. The final act. When that hydrogen fuel starts getting scarce, that whole balancing act we talked about, it just completely falls apart. And the star's ultimate destiny is decided by one single thing, its mass. It's like a cosmic fork in the road. Stars have two very different ways they can go out. Low-mass stars, the ones like our sun, they'll swell up into these enormous red giants before they just kind of gently puff their outer layers out into space. And what's left behind is a tiny, super dense core we call a white dwarf. But the really massive stars, they do not go quietly. They go out with an unimaginable bang. And wow, this image just says it all, doesn't it?
Over on the left, you've got this beautiful, almost peaceful-looking thing called a planetary nebula. That's the serene, glowing remains of a dying low-mass star. And then on the right, you've got the total opposite, the absolute violent chaos left behind by a supernova, which is one of the most powerful explosions in the entire universe. So, in that insane supernova blast, all the star's outer layers get shot out into space. But the core? The core goes the other way. It collapses in on itself, just catastrophically. And for the really, really big stars, this collapse is so complete, so powerful, that it literally crushes the core beyond anything we understand in physics. This unstoppable collapse creates an object with gravity so strong it's like a cosmic waterfall with no bottom. It creates a point of no return. There's this line in the sand called the Schwarzschild radius. And if anything crosses that line, I mean anything, dust, a planet, even light itself, it's gone forever. It can never escape. And that, my friends, is how a black hole is born. And this table here is just mind-bending. It really shows you how ridiculously dense something has to get to become a black hole. To turn our sun into one, you'd have to crush the entire thing down to the size of a small town. The whole sun. And the Earth, you'd have to squeeze our entire planet down to the size of a single marble. It's just wild to think about. And we're not just talking about regular gravity here. The gravity of a black hole is so extreme, it fundamentally warps and twists the very fabric of space and time itself. I love this quote, it really captures it. It creates a one-way door out of the universe. Once you're in, there is no coming back out. Okay, so this is where it all comes together. This is the part of the story that isn't just about what's happening out there in space. It's about us, right here. It's the incredible connection between the lives of stars and our own existence. So let's rewind for a second. When the universe first began, there was basically nothing but the simplest elements, hydrogen and helium. That's it. So where did everything else come from? You know, the carbon that makes up you and me, the oxygen we're breathing right now, the iron in our blood. All of it, every last bit, was cooked up in the unimaginable heat of a star's core, and then scattered across the cosmos in one of those spectacular supernova explosions. And listen, this isn't just some nice, poetic idea. This is a cold, hard, scientific fact. The iron in your blood, the calcium in your bones, the carbon that is the very basis of life as we know it, every single one of those atoms was created inside the fiery furnace of a dying star, billions and billions of years ago. It means that we are, quite literally, made of stardust. We are the children of the cosmos, built from the ashes of stars that lived and died long before the Earth even existed. So, the next time you're outside on a clear night and you look up at the sky, I want you to remember this. You're not just looking at distant points of light. You are looking back in time. You're looking at the cosmic factories that created the very atoms you're made of. You're looking at your own cosmic family tree. Their story is our story. And it really makes you wonder, doesn't it? What other amazing cosmic connections are still out there, just waiting for us to discover them?